Okay, so I just want to start with like sort of introducing this new format and everything. So this is how our sessions are going to be for the rest of the semester, which is kind of sad. It's going to suck not like being able to really get involved anymore, but that's okay because we're going to make it work. So one thing that I really need you guys to do is if you go to the chat option, you can send it to everyone or you can just send it to me, but I need you to send me your UID so I can log this and do my payroll and everything the way that I need to. Just as long as you do that before you leave the meeting, that's all that really matters. So today I'm just going to go over electron configurations, and then I'm going to do quantum numbers and things like that tomorrow, because quantum numbers are just kind of their own thing. It's a whole world, and you really need to understand electron configurations before you can properly do quantum numbers. So I'm going to spend some time on that, and then towards the end I'm going to focus on periodic trends, because it's something she didn't really go over. She was just kind of like, do it. So we're going to go over that just sort of a little bit and have like a Q&A type deal. So I have you guys muted upon entry, but honestly, if you guys could unmute, because I'm going to be asking you questions. I'm going to do this the same way that I would a normal session, where I ask the question, I wait for someone to respond. So that'd be great. So I have not yet posted this handout to my website, but I will right after this session. So this is all about electron configurations, which I know is super exciting. So does anyone have any questions about setup or just how things are going to go? No? Okay. Also, tutoring is still available, so if you feel like you need one-on-one tutoring, we're still doing that. I'm not the chemistry tutor, but I know her. She's really good. She does a good job. So go and figure that out. Call the tutoring office, set that up. You may need that. You may find that you need that more now than you did in face-to-face, just because online is kind of weird and different. And also with online, you have the option to just not, which isn't great, but it happens. So yeah. Okay. So what's the purpose of an electron configuration?
Is it to show the energy levels?
Kind of, yeah. So it's going to, the way that I like to think about it is I like to think of an electron configuration as like GPS coordinates, kind of. They're GPS coordinates for that element and its electrons. How many electrons does it have? What energy level? What shell? So kind of, no, I'm not gonna, I'm gonna put for an element, because our quantum numbers are going to be like our GPS coordinates for an electron. Okay, so now let's talk about sort of reading through these configurations. Let's say you're taking a quiz or an exam, and you sit down, or you're on Newton, and they give you this giant, long deal that's all an electron configuration, and you have to break it down. So typically our electron configurations, one little piece is going to be set up as you're going to have a number, then you're going to have your letter, and then you're going to have a subscript. This is backwards. A number, a letter, and then a subscript number, or superscript, sorry. So what is the number?
N?
It is N. So what is N?
The
The
row.
energy level?
The energy level. The row works until you hit what orbital?
Hit 4.
Yeah, until you hit that fourth row, and in that D sublevel, that's where things are gonna get weird. What about the letter? Ugh. What does the letter show you?
The orbital?
Yes, so it's going to be the orbital. And what are the 4 different orbitals we can have?
S,
S, P,
D, P,
F. S, P, D, and F. So in general, if you were to look at your periodic table, sorry, I don't have like a cool thing where I can like show this. Your S orbitals are going to be these here. So your groups 1 and 2. And then your P orbitals are going to be these last 6 over here. Your D is going to be your transition metals. And then your F is going to be these inner transition metals right here. We don't venture into F often, which is cool because inner transition metals are really weird. They're not really clearly defined. Some of them only exist in laboratory experiments where we make them happen, and they only exist for like a fraction of a second. But they existed, so we put them on the periodic table anyway. So those kind of suck, but we'll work with them. I have a question on here where you have to use it. So, and then finally, okay, the superscript. What does the superscript tell you?
number of electrons.
Yes, number of electrons in that orbital. So what is the Aufbau principle?
Where it fills like each orbital or like
I get you. Are you talking about this thing?
yeah.
Is that the motion that you're making?
Yeah.
Okay, yeah, basically. So the Aufbau principle basically says that an electron is always going, the lowest energy levels, lowest shells, lowest everything is always going to be filled before the next. So lowest energy level and orbital is filled first. But I'm gonna jump around a little bit. Gonna jump down to, just kidding, no, I'm not, I'm gonna wait. So that's the Aufbau principle. It pretty much applies to everything except for 2 very special elements that we talked about. Does anyone remember what they are?
Copper and
calcium.
Cr,
Or is it
Chromium.
chromium.
Right? Cr is chromium, I'm pretty sure.
Uh-huh.
Yeah. So they both start with a C, so that's cool. They both have the same noble gas that comes first in their noble gas configuration, but we're going to get to writing those out in a bit. So first, I want to write the electron configuration for oxygen. So let's do that.
One S2.
1s2, I'm not going to write this, like, I'm not putting this as a superscript because that takes too long, so sorry. So we have 1s2,
2S2.
2s2,
2p4.
2p4. So is anyone like having trouble reading the periodic table and figuring out how to do that, how to write it out? No? Okay, cool. I'm gonna show you anyway because I'm going to upload all of these sessions to my website in case you need to go back and rehear something that I said, or if you have to miss a session. But basically what I typically do is I just I put one finger where I need to stop the element that I want to stop at, and then I just drag my finger across. Like, okay, 1s2, 2s2, 2p, 1, 2, 3, 4. So I just kind of drag my finger across until one hits the other. Okay, how about for phosphorus, a bit of a longer one now.
1s2, 2s2, 3p6, or 2p6,
2p6,
3s2, 3p3.
3p3, perfect. What would be the noble gas configuration for this?
Ne,
Neon.
3s2, 3p3.
3p3, perfect, great. So I really want us to get some experience in working with that d orbital because it's like the tricky one that'll throw you off. So now let's do for germanium. The full configuration.
1s2,
1s2,
2s2, 2p6, is geranium GE?
yes.
3s2.
Okay.
Huh?
3s2 next. Then 3p6.
4s2, 3d10,
Then 4p2.
Perfect. What would be the noble gas configuration?
4 oh.
argon,
Argon,
Then 4s2, then 4p2.
ooh, skipping part.
3d10,
Oh, 3d10. Oh, my bad.
3d10, and then 4p2. So whenever you're doing your noble gas configuration, you basically just kind of cut out all of this, and even though you have that 3 energy level here, anything past this point is going to be written out.
So would the valence electrons for that be 4?
Yes.
Okay.
What about valence electrons for phosphorus?
5.
5. And for oxygen?
6.
6. So the ones that you have in your S and P block are going to be the easiest to find valence electrons for. You can either figure them out through this electron configuration, or you can come and look at the group numbers because it's going to be the same as when we figure out, what do you call it? Oxidation numbers, like how every group has the same. That group number, it's not the one that we worked with because like fluorine is -1, but it's in group 7A. But if you remember the group numbers, if you remember to skip the transition metals and you remember to go 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, that'll tell you exactly how many The number before the A will tell you exactly how many valence electrons everything in that column has. Okay, what are the two major exceptions to the opt-out principle that we discussed earlier?
The copper and the chromium.
Yes, copper and chromium. What is the noble gas configuration for copper?
What? Argon?
Argon?
Is it 3s2?
No.
4s2.
4s2?
1.
4s1.
Is it because it loses the electron?
Um,
What is
It
it?
basically gives 1 to the D.
To make it equal. To
yeah.
make it full. So it'd be
Yes.
3d10.
Yes.
Oh, fuck chemistry.
So this is really, really weird. I'm not gonna lie to you. When I took chemistry, this tripped me up a whole lot. It was just an odd concept and hard for me to wrap my head around. But basically, it's just for stability and sort of like all you need to.
My tutor said it's because they greedy. They
That's
want
fair.
what they want.
But honestly, the way that I got through it was instead of trying to sort of reason through it in my head when I got a quiz question or a homework question, I just memorized these. I straight up memorized, this is copper, this is its configuration, this is chromium, this is its configuration. And I just memorized those, and I knew that every other configuration, I could just look at the periodic table and figure it out. And these were the only two that I had to memorize. So what about chromium?
AR 4S1 3D5.
Yes. So notice how here the D orbital is completely full, and here it is half full. And so the idea is that this is a more stable configuration than having it missing that one. Okay. So if you have like a spare periodic table or some like a file you could download from the internet, I would just go ahead and like highlight those two. Chromium is here and then copper is here. I would just highlight them and try and remember that. And honestly, one of the best ways to begin studying, especially these types of memorization things, is to make flashcards. If you guys didn't know, I have a Quizlet account on my website, and it's not just for chemistry. I tutor biology, so I have a lot of bio 1 and 2 things on there if you're in either of those classes. So I'm doing my best to try and help you guys in this way, but it's a bit harder to make flashcards for chemistry because a lot of it is math and concepts, not so much memorization, but this is one of those times that'll definitely help. So why are these exceptions? Stability, we discussed that.
Have you ever taken an online test before to the point where you have to explain your answer, like you're saying?
I honestly never have. This semester I was actually scheduled to take my first online class for the second 8 weeks, and now all of my classes are online classes. So I've never had to do it before. I don't totally know how they're going to go about it. But because of this, I do have to contact Miss Adams a lot more often. We're in more frequent communication with each other. So I'll try and figure out what she's looking for in terms of setup of the exam. Obviously, I can't go into questions about the content, but as far as how she plans to set it up and things like that, I'll definitely try and figure out what I can to better prepare you guys. I'm also still going to hold test preps here through this. Still 2 hours max. Our test preps tend to fall around at an hour and 45 minutes. But I don't know. I guess we'll see how this works out. But I'll do my best to prepare you. And as I've done in the last test prep, I still have all of my old exams from when I took this class. And I asked her if she minds if I pull questions from there. And she was like, please do. So I'm still going to keep doing that and incorporating those. So I'm going to do my best.
Have any of y'all done your lab?
Yeah, I did a lab today, or yesterday. It was not good. Like, they had so many problems with it. They didn't even upload it on time. And, like, our PDF was messed up to where you couldn't edit it. And, like, I think they're just having a really hard time putting everything online now.
Yeah.
So they've moved your labs online?
Yeah.
But we don't have to do experiment 10, so there's that.
Okay, the what, like the project one?
Yeah.
Okay.
They said that they're gonna like video them like doing the lab, and you just have to kind of fill out like.
Yeah, there's literally no point of even watching the video. Like, I watched it, spent so much time on it. Like, the PowerPoint gives you all the information. The video doesn't do anything, but yeah.
Even though your lab setup is a lot different than when I took the lab, if you guys have any questions, you can always feel free to message me through Remind. That's totally fine. I'll help to the best of my abilities when I can. So yeah, I'm here for you guys. This is a rough transition for like everyone, myself included, but we're in this together and we got this. I'm sorry if you guys hear other people talking. I'm like in my hall's community room, so just doing my best. So let's define an isoelectronic series. She only went over that like once. Oh, but it is an important concept. I know on either a past exam or a past quiz, I had a question where it was like, which of these is an isoelectronic series? And then it had several different options, so.
Isn't that when the electron's charge is changed, so it basically equals another element?
Yeah. So it's going to be a group of elements that have lost or gained electrons to have the same electron configuration. So in this, you could have one element that is neutral and everything else changes to meet that. Or you could have a handful. Let's say you have fluorine, oxygen, and nitrogen all change to meet with carbon, which isn't in your series, but they're all still equal to each other. Does that make sense? I hope so, because that's a weird concept to try and explain. Okay. So let's write, from now on, I'm transitioning from full configuration to noble gas configuration, because that's the one that's hit upon a bit more heavy, and in my opinion, it's one that can get a bit trickier. So let's write out the noble gas configuration for selenium 1-. Okay.
Argon,
Argon,
4s2, 3d10, 4p5.
yes. Why is this 4p5 and not 4p4? Because 4p4 is where it falls in line on the periodic table.
Because it gained an electron.
Because it gained an electron. So we treat it as what element?
Krypton. Or
Bromine.
bromine.
Bromine, yes. So that means that Se1- is isoelectronic with Br. Does that make sense? Does that sort of help put isoelectronic into perspective? Okay. So now let's write the noble gas configuration for Hg2+. So what is the noble gas that comes before mercury?
Where's Mercury?
Xenon.
Xenon.
Oh, it's old.
Okay, now what?
5s2 or 6s2.
Yeah.
Oh, I heard 5.
4f14. 7.
Yes.
5d10.
5d8.
5d8. 5d10 would be correct for a neutral atom of mercury, but it's this 2+ that changes it to 8. Whoa. So what element is this isoelectronic with?
Platoon.
Lead.
What was it? 11?
Platinum.
Oh, that's
Oh, platinum.
He went forward too.
platoon.
Platinum. Okay. So that's all I have on the worksheet, but now I want to move to, okay, how do you guys feel about electron configurations? Good? Bueno? How do you feel about isoelectronic series?
Let's work on those.
Okay. And then how do you guys feel about periodic trends?
We need to go. I need help.
Okay.
That video she posted to like watch.
Did not help.
Oh, I thought it helped.
I did not think it helped much.
So for the video, does it go over all the trends on the paper that she gave us?
Except
Yeah.
2 of them.
Is it this sheet?
Yeah.
Uh-huh.
Would it help you guys if I shared my old notes?
Yes,
Yes.
please.
Yes.
Okay. Because this is from a different textbook. Personally, I do not like
That's
OpenStax.
not
I think it's
funny.
weird. So this is from the old textbook that I used. I like that one a lot more. So I'll share this on my website later today. Okay. So let me figure out. Okay. So you know what? Maybe I should have cut that up. Yeah, I should have cut that up. Let's do that. Okay. So I want you guys to take vanadium, manganese, and zinc. And I want these to be isoelectronic with cobalt. How would the charges of those elements, those three, change to meet cobalt?
For manganese.
You take away 4 electrons from vanadium to get
So,
cobalt.
so for vanadium, you're going to add 4 electrons, which is going to make the charge -4. Does that make sense?
Yeah.
So then for manganese, you're gonna add 2.
Okay.
Then zinc, you're gonna remove 3.
Manganese, you're going to add 2 electrons, so what's that going to make the charge?
Plus.
-2.
2 minus. Because we're adding a -1, right?
Yeah.
And then manganese, we're taking away 2 electrons, yeah?
3.
3, just kidding. 3 electrons. So what is that going to be?
3 plus.
3 plus. Oh, that was supposed to be, you guys get it. So next, I want to take zirconium. Rubidium or rhodium, just kidding, rhodium, and strontium, and yttrium. And I want all of these to have the electron configuration of, let me figure this out. So noble gas configuration of krypton.
Do you mean SR instead of ST?
Yes, I don't know why I put SR or ST. Yes, SR. So krypton 5s2, 4d5.
Would zirconium go -3?
Yes.
RH would be +2.
Mm-hmm.
Strontium would be +5 or -5.
-5, yes.
Y would be 4 minus.
Yes. So does everyone understand how those came to be?
No.
No? Okay, that's fair. It's fair. So what you're going to do is you're going to take a look at your periodic table, okay? And so looking at, ignore the elements I'm asking you to work with first. Let's just look at this electron configuration. So following this electron configuration, we're going to go to krypton. Now we're going to go through 5s2, and we're going to go to 4d, 1, 2, 3, 4, 5. What element are we at?
Roofing. Tet. It starts with the T, right?
Yeah, TC.
TM.
We're at TC. So keeping your finger there, you're going to go look for zirconium, the first one I gave you. Looking at that, how many spaces away is zirconium from TC?
Oh, minus. Oh, okay. I didn't get like when you put the A, like you're supposed to go from krypton and then you go to like the next. That's what I didn't understand. Okay, I get it
Okay.
now.
Does that work?
Yeah, I got it.
And then for those of you that get mixed up between whether it should be a plus or a minus, what I like to do is, okay, look at it. And if you have to, okay, look at TC, which is the electron configuration I've given you, okay? And now we're looking at zirconium. Do you have to go back or forwards?
Forward.
Or to get from TC to ZR?
Oh,
Or do you
back.
go, yeah, so you're gonna go to the left. And so whenever it comes to positive and negative, I really like to think of a number line. So if you just put an imaginary number line there, you're moving back 1, 2, 3. So you've kind of moved to -3 if you're imagining that TC is 0. If that helps.
We were doing krypton.
I mean for this here, for finding the charge of zirconium that would get it to equal this.
Oh,
But reading this, you're going to start at krypton, and then you're going to go to the next row, and then you'll continue reading across. So one important thing in noble gas configurations is, I don't know if she'll try and like pull this on you. I hope not. But if you were to get something like argon, and then, what is it? 4s2, 3d10, right? No, 5. Yes, no, I'm right. I'm sorry. 3s2, 3d10, 4p6, 5s2, 4d5. This is an incorrect noble gas configuration. Technically, it's right, but it's right in that you can read it and figure out where you're going, but that is not the proper way to use the noble gas configuration because we hit a P6 here. So that means we have to go with whatever this is and then continue. You can't start 2 or 3 noble gases behind and then keep writing. So just if that shows up on Newton or on a quiz or an exam, this is wrong. Very wrong. Okay. How do you guys feel about isoelectronic series now?
Better.
Better? Okay. Are you ready to move on to periodic trends?
yes.
Okay. So this is just a, so I'm going to stop sharing now. I'm going to make a poll that I want you guys to answer. Can I not? Cancel. Okay. Oh, what the heck? Just kidding. It wants me to do way too much right now, so I'm not gonna do that right now. We're just gonna roll with what's already going on. So let's start with radii. What are the two radii that we're looking at?
Atomic.
Atomic radii
And ionic.
and ionic radii. So let's talk about atomic radii. What is atomic radii?
It's like the atomic radius increasing across the periodic table.
So it's going to increase going towards the metals, and it's going to increase going downwards. So it's going to increase to the left and down. I like that. I should really just keep this on screen share because that just makes sense. So the definition of atomic radii, or at least the one that I have, the one that I worked with, is the distance between the nuclei when two atoms are bonded to each other. So I like to think of like O2, N2, etc., because those are really easy ones to think about being bonded to themselves, and you can sort of think about it. But I mean, really, it could be bonded to anything. It could be NaCl. And in the same way, chlorine in NaCl and Cl2 are going to have the same atomic radii. It doesn't change. So the reason for this is from top to bottom, it has to do with quantum numbers, or it has to do with the quantum number n. Or in layman's terms, energy level. So it really just has to do with how the valence electrons are, how far they are from the nucleus. Does that make sense? Because if you have a 7 energy level, that's quite a bit further out than a 1 energy level, right? And so it's going left to right because of decrease in nuclear charge, which is going to draw the valence electrons closer to the nucleus. So let's think about it. Compare something like sodium to chlorine. What's the difference there? Is sodium a cation or an anion?
Cation.
Cation meaning what?
It's positive.
Yeah, it's going to have a positive charge. And you know that, oh, no, that's bad. Don't listen to that. I'm jumping ahead to ionic radii. But yeah, basically, it says nuclear charge, but that kind of doesn't work with this. But typically, one thing that I will note is that there is nothing in here that is going to increase left to right and increase top to bottom. It's always going to go either how do I want to like do this? This way, it's either going to increase going this way or increase going this way. So nothing will ever increase this way and then increase this way. Or increase this way and then this way, making it like that. Does that make sense? Sort of. I wish I had like a dot cam to work on. Maybe I'll figure something out. So what about ionic radii? What is ionic radii?
Is it the size of an ion?
Yeah, pretty much. Ooh. So your ionic radii is going to be an increase or decrease in size caused by an increase in electron-electron repulsions. In anions, or a decrease by an increase. Oh my goodness. So can you think about why electron-electron repulsions would decrease in a cation?
Because it's more positive?
Yeah, so whenever you have that positive charge, that means you've lost an electron, right? So think about like if you take two magnets and you face both plus ends towards each other, there's a repulsion there, right? But now imagine taking 6 magnets and pushing all of the pluses together. That's a lot more of a repulsion than just 2, right? So forming a cation is like having those 6 and then taking away 1 and making it 5, or taking away 2 and making it 4. And I did not give you the trend for this. I'm sorry. It's going to increase, the atomic radii is going to increase from right to left and top to bottom. So kind of shape. Whatever, I'll figure it out. For tomorrow, I'm going to try and put together a short little deal so that I can draw out arrows and upload it to my website so it's easier to access. For ionic radii, it's a little bit different. It's going to generally increase from top to bottom. And then, so ionic radii kind of has this weird thing going on where, do you see this split? So it splits up our positive and our negative ions, but they both move in the same direction in their own respective groups. So it's going to increase from right to left. So next, let's talk about ionization energy. What is ionization energy?
The amount of energy needed to remove an electron from an atom.
Yeah. So basically, the ionization energy is the amount of energy required to make an ion. So the minimum energy, oh my goodness. The minimum energy required to remove an electron from the ground state, oh my goodness, of the isolated gaseous ion or atom. So is ionization energy going to increase going left to right or right to left?
Left to right.
Left to right. And is it going to increase top to bottom or bottom to top?
Bottom to top.
Bottom to top. So one thing that I kind of like have a gripe about on this like little worksheet handout that she's provided you with is I don't like how it constantly bounces back and forth between increases and decreases. So whenever I do things, I only work with how it increases, because if you know how it increases, you're going to know how it decreases, right? So I only work with increase. That's all I memorize, because by memorizing increase, you've automatically memorized decrease. And it's much easier than like with this ionic radii thinking, okay, it increases this way, but then it decreases this way. You know what I mean? So the reason for this trend is going to be cations are just smaller than their neutral ion or neutral atoms. So remember, a cation, we're removing an electron, right? Well, as you remove, you're going to see the shrinking of energy levels. It's going to get smaller and smaller. Whereas with anions, you're adding them on. So you're just going to see it get bigger and bigger. What? I just jumped back to ionic radii. I'm so sorry. I was like looking at it and that's what I went with. Wow, okay. So let's move on to electron affinity. What is electron affinity? Okay, that's fair. So electron affinity is the energy change that occurs when an electron is added to a gaseous atom. So basically, electron affinity is an affinity for electrons, or an attraction to electrons. So is this going to increase from left to right or right to left?
Right.
It's actually, It's going to increase from left to right with 3 anomalies. And that's going to be our 2A, our 5A, okay, 2A and 8A have an electron affinity of 0. Yeah.
It also shows 5A.
Yeah. So 5A is going to have an electron affinity, but it's going to be smaller than you expect. It's going to have a little bit of an affinity, but not quite. And this kind of falls into what we just talked about with copper and chromium, in that these are just more stable areas to be in. Okay, is electron affinity going to increase left to right or right to left?
Left to right.
Left to right.
Left to right.
You already wrote that.
The increase top to bottom or bottom to top?
Top to bottom.
Look at your sheet again.
It decreases top to bottom. So
Decreases top to bottom. So how is it going to increase?
bottom to top.
Bottom to top. And then finally, electronegativity. This is the really important one that's going to come back and haunt you even in like OChem. It's very, very, very important. If you take away anything from periodic trend section, it's going to be this one that you want. Electronegativity. Okay. So electronegativity is the ability of an atom and a molecule to attract electrons to itself. So, one super, like, unbelievably important thing that you need to know is that fluorine is the most electronegative element. And you need to know that noble gases have no electronegativity. So knowing that fluorine is the most electronegative element, do you think it's going to increase left to right or right to left?
Left to right.
Left to right. Is it going to increase top to bottom or bottom to top?
Bottom to top.
Bottom to top. But this is absolutely a very, very, very important thing that you should expect to see. Yeah, basically, so one really cool thing, and you're going to see this a lot when we start doing like Lewis structures and we start talking about geometry, because this is my all-time favorite example, and I know it's one of Miss Adams' all-time favorite example, is ZE or XEF4, which is xenon tetrafluoride. And this isn't something that really occurs naturally. It only occurs in a lab when we make it happen. And noble gases are so unreactive because they have no electronegativity, right? But we are able to make this because fluorine is so freaking electronegative. That's the only reason we can make it happen. But yeah, this is going to be all of your periodic trends. I was planning this, I felt like we would spend more time on electron configurations, so I'll try and plan out something very short as a warm-up to go over and really reinforce these trends before we move on to quantum. So, but does anyone have any questions for right now?